You guys asked me to review Thevenin and Norton equivalent circuits, superposition, and op amps. And I'm going to do all of those things in the frequency domain. So let's start with the following circuit. We have a 250 angle 0 degrees volt source connected to a 20 ohm resistor in series with a J10 ohm impedance inductor. Here we have a dependent current source that is supplying 0.03 Vx of current. Here we have a 50 ohm resistor a minus J 100 ohm capacitor. And then over here on the right hand side are our terminals A and B. Assuming that, let's say, omega is equal to 500 radians per second. Let's see what this would look like as a Thevenin equivalent circuit in the time domain. So using resistors, capacitors, and inductors as are necessary. Okay. So the first thing that we would do here is find the Thevenin equivalent voltage. So to solve for VTH, I'm going to just make a copy of this circuit. And then we'll talk about the analysis that this would entail. Okay. So our goal here is to figure out what this voltage is. We can see very obviously that the Thevenin voltage is just the voltage drop over the minus J 100 ohm capacitor. So what I am going to do here is that I've got two things that I am thinking about here. The first is that modified Kirchhoff's current law. So effectively, if I made this node my ground, and I'm missing the voltage Vx, which is pretty important for you guys. Sorry about that. So if I make this nodal voltage, let's use Vy here. If I solve for that nodal voltage Vy, I can then use voltage division to get Vx pretty easily. Because I'll know the voltage drop across my current source, and then from there I have a known voltage over the 50 ohm resistor in series with the minus J 100 ohm capacitor. Another thing that I am entertaining the idea of doing would be a source transformation on the left hand side, so converting that 250 angle 0 degrees volts source that is in series with the 20 plus J10 ohm impedance into a current source that is in parallel with that impedance. From that, I could pretty easily calculate the voltage, essentially the same voltage Vy, and then use voltage division. So which way would you guys prefer? Source transformation or just solve for Vy? All right, so solving for Vy, I'm applying Kirchhoff's current law at node Y. And so this is going to look like Vy minus 250 angle 0 degrees volts divided by 20 plus J10 ohms minus 0.03 Vx, and we'll have to do something about that in a moment. Plus Vy divided by 50 minus J 100 ohms is equal to 0. So right now, I have a problem in as much as there are two unknown quantities. And so I couldn't solve this algebraically. If I wanted to, I'd have to use a computer. But there is a simple relationship between the quantities Vx and Vy that I can exploit, right? So since Vx is simply Vy times minus J 100 ohms over 50 minus J 100 ohms, we can substitute that relationship in, and now we have everything in terms of a single variable. So I would substitute this in right here, and what I will wind up having is Vy times, so let's see, I'm going to have 1 over 20 plus J10. I'm going to have minus negative, so that's going to be plus 0.03 times J100 over 50 minus J100. What I was hesitating about there was the units, because I have J100 ohms over something in ohms is giving me a dimensionless quantity. Over here on the left, I have 1 over ohms, but the units of the 0.03, because they are converting a voltage to a current, are amps per volt or 1 over ohms. So it's the same units on the left term as it is on the middle term, just a way for me to make sure I'm doing this correctly. And then finally, I'll have 1 over 50 minus J 100 ohms. And this will be equal to 250 angle 0 degrees volts divided by 20 plus J 10 ohms. And now I can throw things into my calculator and solve for Vy. So give me just a moment here. So 1 over 20 plus 10i plus, let's see, 0.03 times 100 I over 50 minus 100 I plus 1 over 50 minus 100 I. So I got A to be just 1 over 50. This guy right here is what we're going to call B. And by the way, if you guys got something else, it's always a possibility I typed something into my calculator incorrectly. Please let me know. B is 250 over 20 plus 10i, which comes out to be, goodness gracious, 10 minus 5, 10 minus J5. Amps, and therefore Vy is 10 minus J5 amps over 1 over 50 ohms. Let's see, option, trying to remember where the buttons are on this particular calculator. 559.017. Angle negative 26.565 degrees. All right, so that was the Thevenin voltage. Not a whole heck of a lot different than what we did in class on Monday. We did have to make a substitution there to get it in terms of a single variable. So I chose a method that would work for. Let's start there. If this were literally a slightly more complex, we would have had to have used the computer on this problem. From this, our Thevenin voltage is the exact same thing as our voltage Vx. So that is simply Vy times minus J 100 ohms over 50 minus J 100 ohms. So let's see, so alpha A multiplied by minus 100 I over 50 minus 100 I . 500 angle negative 53.130 degrees volts. Now let's solve for I Norton. So to solve for I Norton, I'm going to copy my circuit down here again. Excuse me. Let's do it on the next page, actually, so that I have enough room. So here is my original circuit, except that I forgot to put Vx on it. When I short circuit these guys, my Norton current is the current flowing through the short circuit. What does this force Vx to be? Which means this current source here is effectively an open circuit. So from this, I Norton is going to be 250 angle 0 degrees volts divided by 20 plus J10 ohms. That's the impedance here. Plus 50 ohms. None of the current is going to branch off and flow through the minus J 100 ohm capacitor. All of it will flow through the short to the right. So that's going to be 250 over 70 plus 10I. Which looks like 3.536 angle negative 8.130 degrees amps. Is everybody okay with the analysis that I've done here? Anything seem weird? Anybody not understand why I can just use Ohm's law effectively to solve for my Norton current for this circuit? All right, so from here, our Thevenin impedance is simply the ratio of our Thevenin voltage divided by our Norton current. And I'm going to express this in rectangular form for a very specific reason. Okay. So let's see. A divided by B, I get 100 minus J 100 ohms. This is the real part of ZTH, and it represents the impedance caused by resistors. This minus J100 is the imaginary part of ZTH, and it represents the impedance that's caused by capacitors. And I'm saying an equivalent capacitance here because the reactance is negative. So if this sign right here were positive, it would look like some inductor value. Because it's negative, it looks like some capacitor value. So we know that 100 ohms is equal to 1 over omega C. So from this, C is equal to 1 over omega times 100, where omega was 500 radians per second, I believe. So 1 over 500 times 100 is 20 microfarads. And from this, let me give myself enough room here to write things down. The Thevenin equivalent circuit is VTH. Let me find where I have that. So 500 cosine 500t minus 53.130 degrees volts in series with 100 ohm resistor in series with a 20 microfarad capacitor in the time domain. In the frequency domain, we would just have 500 angle negative 53.130 degrees. Let's call this a generic impedance having a value of 100 minus J 100 ohms. Any questions, comments, or concerns? Yes. Sure. So let's do the test source method one. Here. Again, just pulling a random problem out of this textbook, bringing a different textbook every damn day so that we're just mixing things up. So for this one, let's say that terminal A is over here on the left, terminal B is over here on the left. We have a 400 nanofarad capacitor. Here we have a dependent source that is 5ix. Here is a 600 microhenry inductance. Here we have a 30 ohm resistor. And our current IX is the current flowing up there. Our angular frequency, omega, is given as 100 kiloradians per second, and we want to find the impedance, effectively the Thevenin equivalent impedance of this network. So the first thing that we would have to do would be to convert this from the time domain into the frequency domain. We don't have any real voltages or currents to worry about other than IX will now be a phasor current IX. So here's A, B, since the impedance of our resistor does not change, I'm going to go ahead and write that one down. So the impedance of our inductor, ZL, is going to be J omega L. So that is going to be, let's see, 100 times 10 to the 3 times 600 times 10 to the minus 6. Looks like J 60 ohms. The impedance of our capacitor is 1 over J omega C. So that is going to be 1 over 100 times 10 to the 3 times 400 times 10 to the minus 9 minus J 25 ohms. And now we need to apply our test source. So I'm just going to move these guys up. All right, so I'm trying to think about how we would wind up doing this, or if it's possible to do this without using a nodal analysis or mesh analysis here. So this dependent source here, its position is what's throwing us a little bit of a wrench here. So let's say that this is a homework problem and that nodal and mesh are fair game to make our lives a little bit easier here, okay? So if I were working this problem from the perspective of having access to a computer algebra tool, I would probably choose to use mesh analysis here. So I would put a 1 angle 0 degrees volt test source here, where this current is my test current that I'm trying to measure. This would be my mesh current IA. This would be my mesh current IB. And from here, I just need to write my two KVL equations, right? So I would have negative 1 angle 0 degrees volts plus minus J 25 ohms times IA plus 5 IX plus J 60 ohms times IA minus IB is equal to 0. Then I'd have J 60 ohms times IB minus IA plus 30 ohms IB is equal to 0. And obviously, could have done this first if I was following my own directions. IX is negative IB. Solve, solve, solve. And then the ratio of 1 angle 0 degrees volts to whatever we find for I test, which is the exact same thing as IA, would be our pattern equation. And we could do that using MathCAD or any other computer algebra tool. I'm sure we could figure out a way to brute force making this work, but we'd have to be pretty creative, and I don't want to spend 40 minutes on this one problem. But effectively, the rules are exactly the same as they were in the time domain, or for DC circuits and all that kind of jazz. Daniel. No, nothing at all. You can solve the system of equations by hand, trying to use substitution if you so choose. You could also use Kramer's rule to set this up as a system and solve it out that way. The only problem with that is the time that it takes. On an exam, it will just take too long. So I would argue, because me, a jackass with a PhD, can't see a pretty obvious way to make this fit using source transformation, KCL, KVL, that kind of thing, I wouldn't put something like this on your test, because it would just take too long for you to solve this one single problem. But the rules for solving it in a homework set, something like that, are the exact same as they were when we saw it in our DC circuit analysis. All right, so now let's do superposition. So let me find a circuit here real quick. All right, this one's relatively straightforward. I'll just make up a number. So let's say that we had the following circuit where we have a 20 angle 10 degrees volt source. Connected to 5 ohm resistor that is in turn connected to a 50 ohm resistor in series with a J150 ohm capacitor, or excuse me, inductor. Over here, we have a 120 ohm resistor connected in series to a minus J40 ohm capacitor. Here we have a current source, 6 plus J 3.5 amps. And we are interested in determining this phasor current, IA. So the first thing that I want to point out here is that we could absolutely do this by setting this node to be ground, solving for the nodal voltage at the top, and then using Ohm's law. Instead, we are going to solve this using superposition, just to remind you guys of what superposition entails, okay? So we're going to solve this guy twice, first with the voltage source on and the current source off. And so that's going to look like this guy, 20 angle 10. just going to write this as a generic impedance that is 50 plus J150. The generic impedance here that is 120 minus J40. And this is the current IA that I am interested in. So a couple of different ways that we could approach this would be to find the equivalent impedance of these three impedances. The voltage divided by that equivalent impedance would give us this current, and then we could use current division to find the current flowing through IA. We could perform a source transformation on the practical voltage source on the left-hand side of the circuit and then apply current division. We could also use voltage division to find this voltage drop, and then this voltage divided by 50 plus J150 would give us the current IA. So there's three different ways that I can see right off the bat of how I would solve for this quantity. You guys choose your own adventure. Tell me which one you want me to do. Source transformation. All right. So source transformation. So I'm going to call this thing ZM and this thing over here ZR for middle and right, just for math's sake in a moment. So source transformation for this would look like a current source up. 20 angle 10 over 5 is going to look like 4 angle 10 degrees amps. And then we have a 5 ohm resistor in parallel with ZM in parallel with ZR. Current we're looking for is this current IA. And this actually should be IA prime since this is a superposition iteration. And we could say that IA prime is 4 angle 10 degrees amps times 1 over ZM divided by 1 over 5 plus 1 over ZM plus 1 over ZR, whatever that came out to be. Then we would work the problem again with the voltage source off and the current source on. So we would have our voltage source turned off with a short circuit. Here's our 5 ohm resistor. Here is, sorry, let me draw this as a generic impedance. Bless you. ZR. Here's our current source direction down, 6 plus J, 3.5 amps. Here's the current IA double prime that we're solving for, and we could once again use current division here. IA double prime would be 6 plus J 3.5 amps times 1 over ZM 1 over 5 plus 1 over ZM plus 1 over ZR. Which of you noticed my mistake? What am I missing? This one was actually intentional. There we go. So the expectation here is that when this current flows down, it will branch off and flow up through these three impedances in parallel. IA double prime is defined as in the down direction, so we need to make sure to include a negative sign to account for that. And then we would put these results together and say that IA is IA prime plus IA double prime. Like I said earlier, this particular circuit would probably lends itself more towards doing that modified nodal analysis where we only have really one unknown voltage to solve for, and then we could use Ohm's law. Superposition is a good tool to have if you have, I would say, 3 or 4 sources. But for 2 sources, most of the things that I can give you can be solved using that modified nodal. All right, lastly, let's talk about an op-amp circuit. So how annoying do you want this to be? As annoying as it'll be on the test. As annoying as it could be on the test. All right. Challenge accepted. It's not going to be that bad. All right, so our goal here is going to be to solve for the quantity Vx. Okay. So we're going to apply the exact same process that we have always applied, but because we're not solving for the voltage at the output node directly, there's going to have to be one additional step at the end to relate V out to Vx. Okay. So we know that this current is 0 amps. We know that this current is 0 amps. This voltage right here, V plus, will be what? I'm not looking for a numerical answer, just tell me how to solve for it. Which impedance? I disagree. So the reason why I disagree is because that would be giving us this voltage, which is not the voltage drop between this point and ground. It should be that one angle 15 degrees current source times 5 plus J2 ohms, because the 5 plus J2 ohm resistor is between the non-inverting input terminal and ground, and we're looking for the voltage drop at the non-inverting input terminal with respect to ground. So throw this in our calculator real quick. I get 5.385 angle 36.801. All right. Now that we know what V plus is, we know what this voltage V minus is because it has to be equal to V plus. So we can write a Kirchhoff's current law expression. So that's going to look like, let me label something over here. this node has a nodal voltage of V out with respect to ground. So this is going to look like V plus over 10 plus J2 ohms plus V plus minus V out over 6 plus J8 ohms is equal to 0. If we are doing the kind of 3-step process or whatever, another thing that I could do, for those of you that paid attention on the second day that we covered op amps, is once I know what this voltage V plus is, I can effectively treat this as a non-inverting amplifier. So this should be the exact same thing as V out is equal to 1 plus 6 plus J8. What the heck happened? Over 10 plus J2 times V plus. Algebraically, they should come out to be the exact same thing. Or answer, hold on. Answer, store A, and then A times 1 plus 6 plus 8 I over 10 plus 2 I store SB. Give it to me in polar. Either way, I should get V out is equal to 9.963 angle 57.497 degrees volts. And then from here, I can just use voltage division to get Vx, where Vx is going to be V out times 3 minus J1 over 5 minus J7 plus 3 minus J1. And I'm going to throw that part in my calculator real quick. 3 minus 1 I over 5 minus 7 I plus 3 minus 1 I. All of that multiplied by the thing I have stored as B. Convert that to polar form. 2.785. Angle 84.08, excuse me, 84.06 degrees volts. That's about as hard and mean as an op amp problem I could throw at you. You can obviously solve it using the 3-step process, or if you can break it down into things that you recognize, like I did. So effectively, let me show you how I looked at this thing. I looked at this and said, that part of it is a non-inverting amplifier, and a non-inverting amplifier behaves using this relationship, which we discussed in class. So as soon as I can figure out what voltage is applied directly to the non-inverting input terminal, then I can just use that relationship and I don't have to do any algebra or anything like that if I don't want to. You're not required to memorize any of those things. You can absolutely do this using the 3-step process. I wanted to not bother doing the algebra that was involved in this KCL equation because I know that it's going to come out to be this thing after 2 to 3 steps anyway. So that was just me being lazy to try to make this faster so that we have time to do the lab.